So this is ECE 2K2 Exam 1. Before I get into it, I just want to add that I have the blank document with no answers and one with answers in the description as PDFs. Okay, starting off with question 1. A cross-section of an enhancement mode PMOSFET is shown below. Find the correct combination of VGS and VDS that biases the device in saturation. So the critical information here is that we have an enhancement mode PMOSFET, and they want us to describe it in saturation. The answer they want is going to be in the form of these saturation inequalities. And the best way, I think, to kind of explain where these come from is somewhat graphically using the IV curves. So to draw those, we're first going to want to remember what we know about an enhancement mode PMOSFET, because what this question is really asking is, do you know what an enhancement mode PMOSFET is? So for any PMOSFET, we know that the drain current is going to flow from source to drain, which means the current is flowing this way. If that's the case, we know that Vs must be greater than Vd. The other thing we know, since it's enhancement mode, is that, and it's PMOS, is that the threshold voltage is less than 0. If it was depletion mode and PMOS, the threshold voltage would be greater than 0, but it's not, it's less than 0. And that's all the information we really need to draw these IV curves. So I'm going to get started by drawing the VDS versus ID curve. I'm using VDS because it's what they give us right here. So if we draw that, say VDS on the x-axis, ID on the y-axis, and then we know that since Vs is greater than Vd, and VDS is equal to Vd minus Vs, that VDS is less than 0. The reason I just kind of over-explain that is because we're going to be putting this graph in the left quadrant for that reason. So, same IV curve shape, but it's in the left quadrant now because we're looking at VDS. If we were looking at VSD, then we would actually be in this quadrant like that, but we're not. And a lot of getting these questions right sometimes is about not making those mistakes with the notation. So we could say that we have some saturation point here. That is VDS sat. And we know that since we're in the saturation region, we are somewhere over here. That's saturation. And therefore, let's say that's VDS, somewhere in saturation. We know VDS is less than VDS sat, right? And that is our first inequality. We see right here, for example, that it says VDS is greater than VDS sat, and we know that's wrong. So we can cross this answer out, and this answer, because it has that same wrong inequality, which doesn't match what we just found right here. And then we can cross these two out as well. Okay, now we have 4 remaining possible solutions, and our remaining inequality over here looks at VGS. So I'm going to do the same thing and draw another IV curve. This time I'm going to look at the gate voltage IV curve. If you remember from class, it kind of looks like that. So, and it goes through the saturation points. So if we draw it, we say, let's say VGS is here, ID is here, and we have some threshold voltage, right? And we know, because this is a PMOSFET in enhancement modes, that the threshold voltage is less than 0, which is why I'm putting it to the left of the origin at 0. And we know that's the shape of a VGS ID curve. And lastly, let's just say that wherever our VGS is, it's to the left, of course, of the threshold. It's somewhere over here. Let's just pick an arbitrary point. And at this point, we've basically set up our second inequality, because we can just say VGS is less than V threshold, which is less than 0 at our origin right here. And that is answer number 8. Question 2. A transfer characteristic for an unidentified MOSFET is shown below. Find the statement below that correctly identifies the device. So this question is really similar to how I explained question 1. We see the same VGS ID curve shape, and all we need to do is look at two critical pieces of information. First off, is V threshold greater than or less than 0? And then second off, what happens as VGS gets bigger? So as VGS goes up, does ID go up or down? That's the real question. And if you don't have this memorized, you're confused right now, or just so you don't have to go and look up what every possible configuration would be, I'll just write down. And we know that in NMOS depletion, for example, V threshold is less than 0, but for NMOS enhancement, V threshold is greater than 0. PMOS enhancement, V threshold is less than 0. PMOS depletion, V threshold is greater than 0. And then we can do a similar thing with what happens as VGS goes up. So like we know for NMOS enhancement, the IV curve is going to look like this, right? That's the IV curve. Same with NMOS depletion. But then for PMOS, the IV curve looks like that. And based on what I've drawn right here, and this is really a thing you should have memorized, we see V threshold is right here and it's less than 0. That's V threshold, it is less than 0. And we also see that the IV curve looks like that. This matches NMOS depletion. So yeah, the answer is 3, depletion mode and MOSFET. Question 3, finally we have a numerical problem, which I find a lot easier to explain. In the 4-resistor bias network shown, it is known that VGS equals 3 volts. Find the value of RD in ohms, which places the DC bias point Q at VDS equals VDS saturation. Given the data, V threshold equals 1 volt, lambda equals 0, Kn equals 2, and Rs equals 1250. I do like to write down the circuit information, so Rs right here is 1250. Lambda equals 0, it basically always does. We never have channel length modulation in these problems. And then I'll also write down VGS equals 3, Kn equals 2, and yeah, that's basically all we need to solve this problem. Remember the equation for drain current and saturation, which we were told we were in right here. So we're in saturation. So we know that ID is going to be equal to Kn over 2 times VGS minus V threshold squared. And this is one of the only equations they'll actually give you on this exam, so you don't have to memorize this, but you probably will just from studying. We can actually just plug our numbers in to solve this problem. So this thing is equal to Kn, which we have 2 over 2 times 3 minus 1, because they give us V threshold right here. I'll add that. Squared. This is equal to 4 milliamps. That's ID. ID is 4 milliamps. Now we're looking for RD, and the way we're going to find RD is we're just going to essentially find the voltage drops across each of these components and then figure out what RD is from that, because we know the potential difference across this entire circuit from this point to this point is 10 volts. You can actually just say that's 0 volts, that's 10. I prefer writing it like this. And then, so we know that all of these voltage drops is going to have to sum to 10. So VRD plus VRS plus VDS, that's going to be equal to 10, as I wrote right there. Now, we already basically have VRS because we know that ID is equal to 4 milliamps, and we know that RS is equal to 1250, so therefore VRS is just equal to 1250 times 4 milliamps, 4 times 10 to the negative third, which is equal to 5 volts. So the voltage drop across resistor RS is 5 volts. We can do a similar thing with VRD, even though we haven't fully solved for it yet. We can say that whatever that voltage drop is, it's going to be equal to RD times 4 milliamps, right? And that's just equal to something. We're not quite sure yet. And then for VDS, this one is nice because we were told that VDS is equal to VDS SAT. So we know that VDS is equal to VDS SAT, which is equal to VGS minus V threshold, which we already solved for right here. It's 2. That's 3 minus 1, it's 2. So we know that the voltage drop across this is 2 volts. So if we rewrite this equation down here, we now see that 10 is equal to VRD plus 2 plus 5. Or, in other words, VRD is equal to 3 volts. Now we can take this value right here and we can plug it in to this equation for VRD. And we see that 3 volts is equal to RD times 4 times 10 to the negative third. So basically, RD must be equal to 3 over 4 times 10 to the third, which is equal to 750 ohms, which is answer 5. Question 4. Given the data shown, find the voltage gain AV when VGS oscillates between 3 volts and 4 volts. The saturation current is 1 milliamp when VGS equals 3 volts, and is 2.4 milliamps when VGS equals 4 volts. So what this question is really asking is for us to find AV when the VGS oscillates between these 2 points at 3 volts and 4 volts, kind of these 2 lines. We can say that's delta VDS over delta VGS because things are oscillating. And we happen to know that this is actually going to be equal to delta VDS over 4 minus 3 because we were already given the variation in VGS here as 4 volts to 3 volts. So this is actually just equal to delta VDS, which I hope makes sense because this denominator evaluates to 1. Now that we have that, we just need to solve for delta VDS. It's going to be equal to VDS as a function of ID when ID is equal to 2.4 milliamps minus VDS as a function of ID when ID is equal to 1 milliamp. Now all we need to do is find this function for VDS in terms of ID. We can easily by evaluation see that it's going to be equal to 10 minus 10 over 4 times ID. That's the drain source voltage in terms of current. All we need to do now is plug this into this to get delta VDS, which is equal to AV. So writing it out a little bit more directly, AV is equal to delta VDS is equal to VDS of 2.4 minus VDS of 1. And if we evaluate this, we see that it's 10 minus 10 over 4 times 2.4 minus 10 plus 10 over 4 times 1. This simplifies to negative 24 over 4 plus 10 over 4, which is equal to negative 14 over 4, which is equal to negative 3.5, which is our solution for 8b. All right, on to the next question. Question 5. In the circuit below, find the small signal output voltage Vout. C1, C2, and C3 are coupling or bypassing capacitors. Assume the transistor M1 is biased in saturation. The output resistance R0 is infinity. The transconductance GM is 20. And omega is in the midband or passband region. So the way that we want to solve this problem is first, with any amplifier circuit, we see if we can deactivate our capacitors or short them, which we can because we're in the passband region. So all these external capacitors get shorted. And the second thing we do is we deactivate all of our DC sources. So that's our DC source right there. And by deactivating it, we short it, sending it to ground on both sides. After doing that, we want to identify what kind of amplifier we have. We see that the source of this NMOS transistor has a direct path to ground right there. So this is a common source amplifier. And with that known, we can draw our pi model. To start drawing our pi model, we draw the AC source, which is over here. And we see that it's in series with a 1K resistor. And then we see that there's these two parallel 2 kilo ohm resistors going to ground. So this is our 1K series resistor, and this is a 2K resistor, and this is a 2K resistor. These, of course, can simplify to a single 1 kilo ohm resistor. And that's our gate. And that's our input side of the small signal or pi model. It's common source, so our source is going to be on the whole thing. And now let's draw our drain. So for the drain, we have a MOSFET right here, which is going to be an dependent source, dependent current source, with current VGS times GM. And then we have some resistance on the output. This is Vout. And that resistance is going to be this 4 kilo ohm resistor. And then it's also in parallel going to ground with this 4 kilo ohm resistor. So that's a 2K resistor. And that is our small signal model. One thing to notice is that the current direction in this circuit is going this way through the transistor, or this way. But we've defined Vout kind of opposite to that. So if we want to describe the resistance across this resistor in Vout, it's actually going to be negative ID times R is equal to Vout. In our case, what that's going to look like is negative VGS times GM times our resistance of 2K times 2 times 10 to the third is equal to Vout. Vout is actually what we're trying to solve for, so we've basically solved our problem by writing that. The only unknown here is VGS, because we were given GM, it's 20. And then we know the resistance, so VGS is going to be equal to VG minus Vs, but we know that Vs is equal to 0 because this is a common source. The source is grounded. So this is actually just equal to VG. And VG is just going to be the output of this 1 kilo ohm voltage divider. And that's, of course, just going to be 1/2 times whatever our Vin is. In this case, Vin is equal to 0.2 cosine omega t, which means that Vg, which is equal to VGS, is equal to 0.1 cosine omega t. With that written, what we can see is that we just need to plug everything in. So rewriting V out is equal to, first off, negative VGS. As I solved for right here, VGS is equal to 0.1 cosine omega t times GM, which I wrote right here is 20 times 10 to the negative third, times whatever this output resistance is, which is 2 kilo ohms. And we've solved our problem. If we simplify this, we get negative 0.1 times 40 cosine omega t, which is equal to negative 4 cosine omega t, which hopefully is 7. Question 6. In the circuit below, find the input resistance Rn seen by the signal source Vs at midband passband frequencies. Assume C1 equals C2 equals C3 is approximately infinity, and C gate source is equal to C gate drain is equal to 0 farads. So, as far as the capacitors go, this problem is actually the same as the last one, because we are still in the midband or passband region. This is just another way of saying what we did last time, which is that we can short all external capacitors, and we can ignore any internal capacitors to the MOSFET. So, now that we know that, all we need to find is the input resistance seen at the signal source, which is right here, which means we can just draw that left half of our pi model, and we should have the answer. So if we start drawing it, we see that we have a 50 ohm series resistor. We have a 1 mega ohm parallel resistor with another 1 mega ohm resistor. Remember that we turn these sources off. So this is ground, this is ground. This is the exact same thing we did last time. This is our source, so it's grounded, and that's our gate. As far as this circuit is concerned, everything over here basically doesn't exist. It doesn't affect this input side of the circuit. So we have our 1 meg resistor, 1 meg resistor, and that's the whole circuit. We just need to know what's R in right here. And we can see pretty easily it's going to be 50 ohms in series with these two 1 mega ohm resistors that are in parallel. So that's 0.5 mega ohms, right? This whole thing can simplify to a single 0.5 mega ohm resistor. And that is our answer. It's very simple. That's Rn. If we look, that is right here. And we're good. Question 7. In the circuit below, find the lower bound cutoff frequency, omega L. Assume the transistor is biased in saturation, its output resistance is infinity, and its transconductance is 10 milliamps per volt. Also, assume CGS equals CGD equals 0 farads. So this is a omega L question. We're finding the lower bound cutoff frequency. And when we find the lower bound cutoff frequency, we look at the external capacitors, which is why they told us here that we can effectively ignore those internal MOSFET capacitors, CGS and CGD. We have 3 external capacitors. We can call them C1, C2, C3, and the formula for finding omega L is that it's the maximum value of the inverses of the RC time constants associated with those capacitors. So what we need to do is find the resistance seen by each capacitor, find the time constant, take the inverse, and then do that for each capacitor. And then the maximum value that we find in that process is going to be omega L, the lower bound cutoff frequency. Starting with C1, we can kind of draw an equivalent circuit here and say that C1 it sees a 50 ohm resistor right here. This source we can turn off. Same with these sources, we can ground these like we do in the other problems. And then on the other side, it sees these 2 mega ohm resistors. So what we want to do at this point is we just say that the resistance seen by C1, RC1, is going to be equal to 50 ohms plus it's in series with these parallel 2 mega ohm resistors, which can simplify to a single 1 mega ohm resistor. And to find tau, we just multiply RC1 by the actual capacitance C1. So we can say that tau C1 is going to be equal to 50 plus 10 to the 6th, that's the 1 meg, times 10 times 10 to the negative 6. This value here is just the value of C1, it's 10 microfarads. If we simplify this a bit, we can say that tau C1 is going to be equal to about 10, because this thing can simplify to being about 10 to the 6th, which cancels with that, and we get 10. So 1 over tau C1 is going to be equal to 1 over 10, and that's our first value for this formula. So we can say that we're looking for omega L is going to be equal to the max of 1 over 10, and then 3 more things. Let's find the rest of this statement. For C2, we can draw it down here. We can say it sees this 5 kilo ohm resistor and this 5 kilo ohm resistor, both going to ground. And that's it. You might ask why we can ignore this MOSFET right here, because there technically is this dependent source also as part of the circuit, but we've shorted the AC source and the DC sources, so we know that the voltage associated with this dependent source is going to be 0, because remember, the current flowing through here is VGS times GM, but we know VG and VS are 0, so we know that this dependent source is off. It's an open circuit. And from that, we say that RC2 is just going to be these two 5K resistors in series, so it's equal to 10 times 10 to the third, 10K. So tau C2 is going to be equal to RC2 times C2, which is equal to 10 times 10 to the third times 10 times 10 to the negative 6, which means tau C2 is equal to 10 to the negative first, which is equal to 1 over 10. So if we want to find the inverse of tau C2, we see that it's just going to be 1 over 1 over 10, which is equal to 10. So that's our second value. Lastly, we want to find C3 and the resistance associated with it so that we can find its time constant. So let's get to doing that. If we start to draw C3, we could say we have this capacitor, C3, and this 100 ohm resistor that is in parallel with it. And then we also have this MOSFET here, which actually does become relevant because the source of this NMOS is right here. So we could say that Vs is actually the same as the voltage across the capacitor. The reason that's important is because if this capacitor has a voltage on it, it actually changes what Vs is. And remember that if we draw this dependent source, the current going through this branch is VGS times GM, and now this point is actually equal to Vs right here. So the Vs matters now, and it is creating some complexity, which we can solve by doing an IV test that you learned in 2K1. So what we do is we take this circuit and then we turn this capacitor into a voltage source. So we'll redraw it like this. We'll say we have some voltage source, which is 1 volt, and that's C3. On one side of the voltage source, we have this 100 ohm resistor. And then on the other side of the voltage source, we have our dependent current source. Now, what we can say is the resistance seen at this voltage source is going to be equal to the voltage divided by the current going out, where the current is the sum of, let's say, the branches, I1 and I2. So all we need to do to find the resistance seen by C3 is figure out what these two currents are, find the total current leaving C3, and then just take the inverse. I1 is pretty simple because we can see that we have a 1 volt source going across a 100 ohm resistor, so it's just going to be 1 over 100. And for I2, we know that it's just going to be described by this equation, which is VGS times GM. But we need to be careful here because the direction of this current source, this dependent current source from the MOSFET, is actually opposed to the way that I've defined I2. So we need to call this negative VGS times GM. Now let's think about what VGS actually is. We know that Vs is equal to this voltage source that we've put right here. So Vs is equal to 1 volt. And we know that Vg is equal to 0 because we turned off this AC source here. So we know the voltage at this point is 0 volts. So therefore VGS is going to be equal to Vg minus Vs, which is equal to 0 minus 1 is equal to negative 1. So if we rewrite this, we see that I2 is equal to negative 1 times negative 1 times GM, which is just equal to GM. What is GM? I think they gave it to us right here. It's 10 milliamps, which we could write as, we could say GM is equal to 10 times 10 to the negative third is equal to I2, which is equal to, if we simplify that, 10 to the negative second. So we can say that I2 is equal to 1 over 100 as well. So I1 actually happens to equal I2. If we take their sum, we can say I1 plus I2 is equal to 2 over 100. This is the total current leaving this source. Now we just need to take the inverse to find the resistance because of the equation I wrote right there. So we can say that the inverse of 2 over 100 is equal to R C3 is equal to 50 ohms. And that's the resistance. All we need to do to find tau C3 is multiply 50 ohms RC3 by the capacitance, which is 10 times 10 to the negative 6, 10 microfarads. And that's tau C3. We can then say the inverse of tau C3 is going to be equal to 1 over 500, if I simplify a little bit, 500 times 10 to the negative 6, which is equal to 2,000. That is our answer for our last omega L value. We can see pretty obviously that 2,000 is the maximum value in the set of omegas that we found. So 2,000 is our answer. In the circuit below, find the upper bound cutoff frequency, omega H. Assume the transistor is biased in saturation, its output resistance is infinity, and its transconductance is 10. Also, assume C1 equals C2 equals C3 is approximately infinity, CGS is 50 femtofarads, CGD is 0 farads, and CL is 100 femtofarads. So this is a problem that asks us for omega H, the upper bound cutoff frequency, which is a value related to the internal capacitors, or the really small capacitors. So in this case, there actually is one external capacitor which is of such a small value that we consider it. But you see C1, C2, C3 we can ignore, so that means we short them, just like we did in the other problems. And for CGD, we can ignore it because it's 0 farads. So we only need to consider CGS and CL. To do this, the formula is that omega H is equal to the minimum, the minimum value of 1 over tau CGS and 1 over tau CL. This is very similar to the omega L formula. It's just that it's minimum instead of maximum, and you definitely have to have that memorized. Before we continue, we also want to turn off our DC sources here. So ground to this, and short our AC source. And now we can just draw our two equivalent models the same way we did with our omega L problem in question 7. And we can solve for the resistances seen by each capacitor, find the RC time constant, and then find omega H using this. To start with CL, we can see that on one lead, it goes straight to ground. So if we draw CL, that's CL, one of these just goes to ground. And then the other lead sees a 10 kilo ohm resistor to ground and another 10 kilo ohm resistor to ground. Both of those are in parallel. So we have 10K to ground and then another 10K to ground. I could have drawn that cleaner from the start. Let me clean it up. And that's our circuit. You can see there's really nothing else going on here, so the resistance RCL is just going to be equal to these two 10Ks in parallel, which is 5K. And then tau CL is going to be equal to RCL times the capacitance of that capacitor CL, which is equal to 5 times 10 to the third times, 100 femtofarads, 100 times 10 to the negative 15th. This is going to simplify a little bit, or at least I would say it's simpler to, let's say, 500 times 10 to the negative 12. That's how I'll write it, as tau CL. And 1 over tau CL is going to be 1 over 500 times 10 to the negative 12. So now we can write our first omega L value. We can say that omega H is going to be equal to the minimum of something tau CGS, 1 over 510 to the negative 12th. Now that we solved for CL, let's solve for the gate source capacitor. This capacitor isn't drawn yet, but it's quite simple. We just add it in from our gate to our source. There's an internal capacitor. And if we start to draw our equivalent model, we see that one lead has a short straight to ground through this capacitor C3, which is shorted. So one lead goes to ground. The other lead goes through a 1 meg resistor to ground, another 1 meg resistor to ground, and a 10 ohm resistor to ground, all in parallel. So that's a 10 ohm, 1 meg, and then another 1 meg. We can simplify this a bit and just say that these two 1 mega ohm resistors in parallel are still going to be so big compared to this 10 ohm that we can ignore them, and we can just say that our CGS is equal to 10 ohms. We can say, based on that, that tau CGS is equal to our CGS times whatever that gate capacitance is. So that's going to be equal to 10 times 50 femtofarads. So it's equal to 500 times 10 to the negative 15th. So 1 over tau CGS is going to be equal to 1 over 500 times 10 to the negative 15th. And we can just write that over here. We're looking for the minimum of these two values that we found, and we can see that this one is going to be smaller. So omega h is equal to 1 over 500 times 10 to the negative 12th, or 10 to the 12th over 500, which is also equal to 2 times 10 to the 9th. And that's our answer in radians per second. And it's right here. Oh, circle it better. It's right here. In the circuit below, find V out, assume the op-amp is ideal. So this is an op-amp question, and I was a bit conflicted on how to solve it because I could use a more standard way using KVL or KCL, or I could just kind of do it the way I would do it on an exam. And I opted to do the second one just because I figured you've seen enough KVL and KCL stuff in class. I just thought it would be a little bit simpler to solve it in a slightly quicker, more intuitive, I guess, way. But if it ends up being super confusing, I apologize for that. So, since this op-amp is ideal, we know that this node right here, let's call it VA, this node VB, characteristic of an ideal op-amp, VA equals VB. And then we also know that no current is going to flow into the op-amp through those nodes. What's nice about that is now we know VB because we can solve for VA. We have this voltage divider right here, and then just an input voltage for that voltage divider. These two 20K resistors are just going to split this input voltage in half, so we can say that VA is just equal to 1/2 times 2 cosine omega t, which is just equal to cosine omega t, which is equal to VA, or VB. So now we know that this voltage right here, VB, is just cosine omega t. That's VB. Now what I'm going to do, what I meant by kind of a more intuitive way of solving it, is I'm just going to notice that we can find the current going through this resistor by just looking at the voltage drop from this point here to this point. And then we can use that current and say the current going through this resistor is the same as the current going through this one, and then that current times the resistance here, 50K, is going to be equal to the voltage drop across this. Let's call that V50K. So we'll notice that V50K is just going to be equal to 50K, the actual resistance, times I1, whatever this current is going through this part of the circuit. Now that we have this voltage drop, we'll be able to pretty easily see what the voltage V out is, because we'll have the voltage on this side of the resistor, the voltage drop across it, and we'll pretty easily be able to determine V out. So that's what I meant by a more intuitive way of solving it. So let's just get to that. We know that I1 is going to just be equal to whatever the voltage drop across this 10 kilo ohm resistor is divided by 10K. So we might call that V10K. And I'll say that V10K here is going to be 6 cosine omega t minus cosine omega t, because those are the voltages on both sides of the resistor. So we'll say that it's 5 cosine omega t. Based on that, since we know the voltage drop from here to here is 5 cosine omega t, we know that I1, the current through this resistor, is going to be equal to 5 over 10K, which is the resistance, times cosine omega t. And based on this equation, we know that the voltage drop across this resistor is going to be equal to I1 times 50K, which is 5 over 10K times 50K times cosine omega t. That is equal to V50K. If we simplify this a bit, simplify this, we'll see that V50K is equal to 25 cosine omega t, which means the voltage drop across this component here is 25 cosine omega t. And I'll just write that up here. So from this point to this point, we have a 25 cosine omega t drop. We know that right here, we have a voltage of cosine omega t. And right here, we have a voltage of V out. So, therefore, V50K is equal to V out, actually, cosine omega t minus V out, or 25 cosine omega t is equal to cosine minus V out. And we see, based on this, that V out must be equal to negative 24 cosine, because that's what gets us 25 on this left-hand side. So V out is equal to negative 24 cosine omega t, because cosine omega t minus negative 24 cosine omega t is equal to 25 cosine omega t. That was probably unnecessary. And that's the solution. It's right here, number 9. It's right here, 9. I hope that wasn't too confusing. I just wanted to solve things a little bit differently. Question 10, last question. In the circuit below, find V out, assume the op-amp is ideal. And I'm going to solve this one a bit more conventionally. So I would recommend being able to recognize immediately that this is a differentiator circuit. But if you don't have the op-amp circuit configurations memorized, this is how you would go about solving this problem. You would first say, since this is an ideal op-amp, let's say this is VA, this is VB, VA equals VB, and this is 0 volts right here, so we know this node right here is 0 volts. That's just an ideal op-amp characteristic. The next thing you would probably want to do is write out the characteristic equations for the situation. So we have some voltage V out right here, and then we know that whatever current goes through this resistor is the same as the current through this capacitor. So we could say that capacitor current IC is equal to the voltage drop across this resistor divided by this resistance, 4K. So we could say it's equal to VB minus V out over 4K. Or, nicer way to write that is 4 times 10 to the third, maybe. And we also know, since this is a capacitor, that the current through it is just going to be equal to the derivative of whatever the voltage drop across it is times the capacitance. So that's going to be the capacitance of 1 millifarad, so 10 to the negative third, that's the capacitance, times d by dt of VC, or in this case, d by dt of, what's VC? Well, we see 0 volts on this side and an input of 0.5 cosine t on the other side. So that tells us that all of the voltage that we input gets dropped immediately across the capacitor. So VC is just equal to the input 0.5 cosine t. So d by dt of 0.5 cosine of t. And that is our equation for this problem. At this point, we've really done all of the setting up we need to do. We just rearrange for the solution. So we can multiply both sides by 4 times 10 to the third. And this simplifies a bit to be VB minus V naught is equal to, these cancel, 4 times 0.5 d by dt cosine of t. Do a little bit of more simplification. Remember, VB actually equals 0, so this thing just goes to 0. We get negative V naught is equal to 2 times the derivative of cosine t, negative sine t. And then we just multiply both sides by negative 1, and we get that V naught is equal to 2 sine of t. And that is the solution to that problem. Okay, actual last question this time. I'm going to go through this one a bit quicker because I think you're probably used to the op-amp rules by now. In the circuit below, find V naught of t for t is greater than 0. Assume the initial voltage across the capacitor is 0, and the op-amps are ideal. So we know that this node here is grounded, so this is 0 volts, which means this one's also going to be 0 volts. So the voltage drop across this component, this resistor, V1K, we could call it, is going to be equal to just this input voltage of 0.5 cosine t. That is the voltage drop. We also know the current through this resistor is going to be equal to the current through this capacitor. And at this point, we can use that to essentially find VB. So let's write this out. We know that there's some current through this component. It's going to be the voltage drop divided by the resistance, so 0.5 cosine of t divided by 10 to the third. And we know that's equal to the current through the capacitor, which of course is also the capacitance times the derivative of the voltage drop, Vc. So 1 millifarad, 10 to the negative third, times the derivative of the voltage drop across this component, which on this side you have 0 volts, and on this side you have Vb. So we know that Vc is equal to 0 minus Vb, which is equal to negative Vb. And that is our kind of formula that we just need to rearrange to solve this problem. These 10 to the thirds cancel, and then I'm going to move this negative sign over to the other side, and we're going to say that negative 0.5 cosine of t is equal to the derivative of Vb. Now we just integrate, and we see that negative 0.5 sine of t is equal to Vb. Now right now we have Vb, but we want V out, so we want to check what that relationship is, and really conveniently, This is a non-inverting, just non-amplifying buffer. So all it is going to do is take VB, and then it's just going to reflect VB up on this node. And we see that this goes straight to Vout, so VB actually equals Vout, because this is just a buffer. Which means that our final answer for Vout is negative 0.5 sine t, which is number 4. And that is the whole exam.